So as a quick reminder, what we did in the previous class, we started talking about the operational amplifier, and I told you that the operational amplifier is integrated circuit, and it has 8 different pins, and we are start counting from that pin, which is the nearest pin to that circle. This is the notch that I showed you. It is the starting for counting from that point. So this is pin number 1, pin number 2, 3, 4, and then counterclockwise 5, 6, 7, 8. And in the previous class, I told you that this is the symbol for the operational amplifier. And what we are dealing with, we are dealing only with pin 2, pin 3, pin 4, pin 7, and 6. So pin 7 and 4 are connected to the power supply. So pin 7 is connected to V positive and pin 4 is connected to V negative. So these 2 pins are preparing our operational amplifier to start working or to be able to use it. These are not the inputs. The inputs for the operational amplifier through pin 2 and pin 3. So pin 2 is called inverting inputs and pin 3 is called non-inverting inputs. And we are taking the output from pin number 6. So this is the symbol for the operational amplifier that I showed you in the previous class. We are connecting our inputs through these 2 pins, and we are taking our outputs from that pin. And these 2 pins are describing the power supply. So these are the power supply 4 and 7. And these 2 and 3 are the inputs, and the output is V out, which is 6, pin number 6. In the previous class, I told you that we are dealing with the operational amplifier in the linear region, and we are depending on virtual short condition, which means VP is equal to VN and IP is equal to IN is equal to 0. So IP is the current to the positive input to the operational amplifier, and IN is the current to the negative input for the operational amplifier. And V positive, which is VP, is measured from that positive terminal to the reference or the neutral, and the negative voltage is measured from that negative terminal to the neutral or to the reference. And the output is measured between that pin and between that reference. In the previous class, I told you that please never apply the voltage to the input terminals of the operational amplifier without power supply being connected first. So the steps or the procedures for connecting the operational amplifier in my circuit is: part A, I will connect the circuit without turning on any power supply. Then I'm going to apply the power supply, which is positive, negative 15 or whatever that you have between that and that, again, between which 2 pins, between this guy, which is pin 7, and this guy, which is pin 4. So the first power supply I'm turning it on is the power supply connected to pin 7 and pin 4. And after that, I'm going to apply the input voltage. If I have input voltage to the positive terminal, that's okay, I will apply it. If I have input voltage to the negative terminal, I will apply. Other words, I'm not applying or turning on the voltage to the inputs through pin number 2 and 3 before connecting the power supply for pin 7 and pin 4. If you would like to remove the inputs, please keep the power supply that you have before removing the inputs, and then remove the inputs. And if you would like to remove the power supply after that, that's okay. But don't do the opposite because you will lose your operational amplifier. So I'm not disconnecting the power supply first that's connected between pin number 7 and pin number 4. I'm not disconnecting it first. I'm disconnecting first the input voltage to pin 2 and pin 3. I'm disconnecting that first. And after that, I will disconnect the power supply to pin 4 and 7. And the opposite story, if I would like to connect, I'm connecting first the voltage to the positive, which is pin number 7 and pin number 4. I'm connecting the power supply first, then I'm connecting the inputs. Are you seeing what I'm talking about, guys? This is very, very important to know, and I wrote that in the lab report as well. So please follow the procedures for connecting the operational amplifier to your circuit. In the previous class, we started talking about that problem, but we didn't complete it. So I gave you that operational amplifier. This is very simple circuit. What we have input connected to the negative terminal and input connected to the positive terminal, pins 2 and 3. So this is the input voltage VA and this is the input voltage VB. And for pin 4 and 7, we connected the power supply. Then we have a resistor here connecting the negative terminal to the output, which is called feedback resistor, 100 kilo ohm. And I have another resistor here that's connected between the negative and the source, which is called 25 kilo ohms. What's needed here, I would like to calculate VO. Where is VO? It is the voltage between that point and the neutral. If VA is equal to 1 and VB is equal to 0. So for solving the operational amplifier problem, I'm going to use the regular methods that I was using before from chapter 4 and chapter 2 and 3. So I can use Kirchhoff's voltage law and Kirchhoff's current law. I can use node voltage method. I can use whichever I want. Voltage divider if I can, current divider if I have something related to that. Or any other methods. The only difference is I have to keep in my mind, I have something new in my circuit, which is the operational amplifier. So if we are talking about the linear region, I have two conditions. I'm talking about them. And I'm talking about ideal operational amplifier. So I'm assuming that the internal input resistance for the operational amplifier is very, very huge value. That's why I'm assuming IP is equal to IN is equal to 0. But this is not the practical operational amplifier. This is only for simplicity. I'll show you the practical operational amplifier probably by Wednesday or Friday, and I'll show you how to deal with it. But right now, I'm assuming that IP is equal to IN is equal to 0 for simplicity. And this assumption is acceptable because the error is very, very small. The second thing is I'm saying VP is equal to VN. So these are the two conditions I'm using, and I'm writing them for any operational amplifier. So far, I'm using it before I start solving the problem. Then I will use my regular methods. Let us see where is IP and where is IN. IP is the current at that in that branch, and IN is the current in that branch. So IP is the current connected to the positive, and IN is the current connected to the negative. So what am I going to say? I'm going to say IP is equal to IN is equal to 0, and I'm going to say VP is equal to VN. For VP is equal to VN, I have to define where is VP and where is VN. I have to define both of them. So if you are talking about VP, it is the voltage from that positive to the neutral or to the reference that you have. And VN is the voltage from that point to the reference that you have. Then I will define VP and VN as a function of the input voltage, if I can. If not, that's okay. Leave them right now. So the first step, I'm going to define IP and IN, and I'm going to say IP is equal to IN is equal to 0. The second step, I'm going to define the location of VP and VN and the relation between them and the input voltage, if I can. So if you try to look to this circuit, I can say that the voltage from that point to that point is VP. And I think it is the same like VB. Yes, which is the source voltage to the positive terminal based on the configuration of the problem. So what am I going to do? I'm going to say VP is equal to VB. What's VP? It is the positive voltage for the operational amplifier. What's VB in my circuit? VB is this voltage, which is the source voltage. Any question, guys? Now, where is Vn? Vn is the voltage from that point to that point. Okay, so if I would like to define the voltage for that node, what is the voltage for that node? It is Vn, yes, because you told me that the voltage from that point to that point is Vn, and I'm looking for the voltage for that node. Why? Because I'm going to say summation, the current for each node is equal to 0. So the voltage for that node, based on the configuration of what I have, Vn is equal to the voltage for that node. Now, what about the voltage for that node, guys? It's VA. So what I did here, I wrote VP is equal to Vn, but actually VP is equal to VB. That's why Vn is equal to VP as well. Now, I'm going to say summation the current for that node is equal to 0. Why? Because he would like to calculate VO, and I know that VO is function of the current in this branch. So I can say summation the current for that node is equal to 0. And most of the problems are depending on summation the current for each node is equal to 0. So I will say summation the current for that node is equal to 0. What is the current in this branch, guys? It is Vn minus Vo divided by 100 kilo. And by the same way, the current in this guy is Vn minus VA divided by 25. And I think this is what I wrote here. Vn minus VA divided Vn. Are you seeing that, guys? Well, are you seeing the circuit? So Vn minus VA divided by 25 kilo. And the current in this branch is Vn minus Vo divided by 100 kilo. And the current in this guy is called IN. Then I wrote my equation here, and what I'm going to do, I'm going to substitute by VA is equal to 1, by VB is equal to 0, and based on VB is equal to 0, for part A, I can say Vn is equal to VP is equal to 0. Yes, because VP is equal to Vn is equal to VB, and VB here is equal to 0. So based on the configuration of the problem, I can say Vn is equal to VP is equal to 0. And VA is equal to 1. So I will go back to my equation. Vn is equal to VB, but VB actually is equal to 0. Vn is equal to VB, but VB actually is equal to 0 as well. And VA is equal to 1, and IN is equal to 0. Then I have only one equation and one unknown, which is VO. I can solve that equation and find the value of VO. And this is what we did in the previous class. Any question, guys, for that?
So why do we assume IP and IN are 0?
He told me that based on the assumption that the internal resistance is very, very high value, so I can assume IP is equal to IN is equal to 0 because the internal resistance to the operational amplifier is very huge value, as if it is infinity. Okay? Yes. Please raise your voice.
VP and VN.
VP and VN, yes. They are equal for based on which condition we said here. If you still remember, we said we are dealing with virtual short condition. We are assuming that we are dealing with the linear region, and we are dealing with ideal operational amplifier. So we are assuming that VP is equal to VN. Any other question for that part?
No matter how it's wired, still.
Yes. Any other question? Okay. Now, let me read part B. Part B, he said, repeat A for VA equals 1 and VB equals 2. So I'm going to repeat solving part A. What is in part A? Oops. I have this equation in part A. So what am I going to do here? I'm going to substitute by VA1 and VB2. So I will go to VA, put 1, and VB, go 2, and write my equation again. He told me that this guy is VB, and this guy is VB, and this guy is 0. He told me that VB is equal to what? VB is equal to 2. Let me copy this first, because I will need it for the last step. Now, he told me that VB is equal to, let me go back. VB is equal to 2 and VA is equal to 1. So VB is 2, this guy is 2, and VA is equal to 1. Then I will substitute in that equation, and I will be able to calculate VO because it's only one equation in how many unknowns? In one unknown. So I can solve this problem for calculating VO. If you try to calculate it, I believe VO for part B will be equal to 6 volts. Now I will check 6 volts. Oh, my linear region is in between 10 and -10, so it is in the linear region at that time. It is acceptable value. I'll leave it as it is, which is 6 volts. For part C, he asked me about what? If VA is equal to 1.5, he would like me to repeat solving the problem. But VA at that time is equal to 1.5. And he would like me to specify the range of VB. He would like to find VB that avoids amplifier saturation. Again, he would like me to calculate the range of VB. If VA is given 1.5, that avoids amplifier saturation. What do you mean by avoids amplifier saturation? He means by saying that sentence, please find the value of VB such the range of values for VB. I have more than one value, such that your output voltage, which is VO, in between 10 and -10. This is what he is asking me about, because my linear region is in between 10 and -10 based on the configuration of the problem. So he is asking me if VO is in between 10 and -10. Can you please find the range of VB? It's straightforward. What am I going to do here? I'm going to repeat writing the same equation again. He didn't copy everything. That's okay. So I'm going to rewrite the same equation again, which is Vn minus Va plus Vn minus Vo divided by 100 plus In. And he told me that also Vn is equal to VB, Vn is equal to VB, and In is equal to 0. But the new thing that he gave me the value of VA. Do you remember the value of VA? 1.5. So he gave me that guy 1.5. What about VO? I will solve the problem 2 times. The first time is if VO is equal to 10, which is the maximum value. And then if VO is equal to negative 10, which is the lowest value, based on these two values that I have. So I'm going to resolve the problem. This is one equation in one unknown. So I'm going to find V as a function. I'm going to find VB as a function of VO. So if you try to rearrange your equation, you will find that VB is equal to 1 over 5 multiplied by 6 plus VO. From where I got that equation, I tried to rearrange this guy. So Vn is VB, Vn is VB, and then I have VO. So I have equation in one unknown, in two unknowns, VB and VO. I tried to put VO in one side and VB in another side. Then I got VB equals 1 over 5 multiplied by 6 plus VO. Now, I'm going to say for linear region, VO should be in between negative 10 and 10. And then I'm going to substitute by VO is equal to 10 and find the corresponding VB. And then substitute by VO is equal to negative 10 and find the corresponding VB. And then I'll have range of values based on negative 10 and 10 for VO. So based on that, on the above range of values of VO, I can say VB is in between negative 0.8 and 3.2 volt. If you try to substitute in the equation for VB by VO is equal to negative 10 and 10, you will get the range of values of VB. Any question, guys, for that problem? Okay, we have already solved a very simple problem that is talking about the operational amplifier, and it's telling me how to deal with that operational amplifier. Now, I'm going to talk about different applications for the operational amplifier. We are using that for what? The first application for the operational amplifier is inverting amplifier circuit. So I'm going to use this guy for inverting the voltage. Imagine, for example, I have 10 volts, but I need negative 10. So my power supply is generating 10 volts, but I need negative 10. I need negative 15. I need negative 5, negative 7. How to do that? I can do that by using the simple circuit that we have on the board here, which is the circuit for the operational amplifier, by connecting the supply voltage to the negative terminal. Again, I'm connecting the supply voltage to the negative terminal. And we are calling this guy inverting operational amplifier or inverting amplifier circuit because we have only one voltage source and it is connected to the negative terminal. So I am expecting the output will be equal to constant multiplied by Vs multiplied by negative sign. Again, I am expecting the outputs will be equal to negative constant multiplied by Vs. That constant, we are calling it gain. So right now, I'm going to derive the relation between the output voltage and the input voltage. The input voltage is Vs and the output voltage is Vout. Imagine we have that operational amplifier. This is positive VCC and this is negative VCC, and I have RS, and which is the source resistance, and I have RF, which is the feedback resistance, and we have a current here which is IF, and we have a current here which is IS. What do you want? I would like to find the relation between the input voltage and the output voltage. And I would like to prove that this relation is equal to negative constant. And this constant, we are calling it gain. Let us see. So before I start proving that, or before I start deriving the relation between the output and the input for the operational amplifier, I have to define IP and IN. What is IP and what is IN? And what is VP and what is VN? So if you try to look to the circuit, this guy is called IP. And this voltage is called. So what is the value of VP? Oh, I have a wire without resistance, so I'm expecting VP is equal to 0 because there is no resistance. So the voltage drop across that branch is equal to 0. And you told me VP is equal to VN. If VP is equal to 0, VN is equal to yes. So for that configuration, I can say also VN is equal to 0. For that configuration only. I'm dealing with each problem by saying from the beginning, VP is equal to VN, IP is equal to IN is equal to 0. Then I will figure out what's VP and what's VN. Here in our problem, VP is equal to 0. Based on that, VN is equal to 0. In the previous problem, VP was equal to VB. That's why I told you VN is equal to VB. Now, let us define IN. Where is IN? This guy is IN. And the voltage from, imagine that this node is called in. The voltage from that point to that point is called VN. So the voltage for node N is equal to VN. So the voltage for that node is equal to VN. What about the voltage for that node? It's equal to VS. I will repeat writing my equations again by saying VP is equal to VN and IP is equal to IN is equal to 0. And based on the configuration of the circuit, since VP in that circuit is equal to 0, so I can say VN is equal to 0. I'm not saying that for each problem, for that configuration only. Are you seeing what I'm talking about, guys? Any question? Let us say summation of the current for each node is equal to 0, and I have different currents. I have this current, I have this current, and I have this current. So I'm going to say summation I is equal to 0 for each node. Summation for each node, I have only node N. That will solve the problem. So the current in RS is equal to VN minus VS over RS plus the current in this guy is equal to VN minus VO divided by RF plus the current in this guy, which is IN, equals 0. You told me at the beginning that VN is equal to VP and VP is equal to 0, so I can say VN is equal to 0 as well for that problem. Then I know also IN is equal to 0. Then based on that, I can find a relation between VO and VS, and I can rearrange my equation. If you try to rearrange your equation, you will realize that VO is equal to negative RF divided by RS multiplied by VS. Based on that, I can say VO over VS equals negative RF divided by RS, and this is the relation between the output and the input. And I told you that V output over V input should be equal to negative times a certain constant, which is RF over RS in our case, which is the feedback resistance, which is this guy, divided by the source resistance. So we are calling that RF over RS as gain of my circuit. That's why I told you that this guy is called inverting operational amplifier. Why it's called inverting operational amplifier? Because the output is equal to negative constant multiplied by the input, or negative the gain multiplied by the input. Any question for that? Let us solve. Yes. No, Vn is the voltage from that terminal to the reference. And Vp is the voltage from that terminal to the reference. But the input voltage is the voltage between that point and that point. Okay. Any other question? Yes. I have a question. Okay. Yes, go ahead. Canceling. Could you please repeat the question? This resistor absorb the voltage? No, there is a voltage drop across this guy due to that current. And this voltage drop is reducing the voltage that will arrive here. And based on our circuit, since that voltage is zero, it means that this guy is absorbing what we are having here. For that problem only. So you are talking about this equation? I told you at the beginning that VB is equal to Vn. And based on that, I can define Vp and Vn. So if you try to look to this circuit, the voltage from that guy to that guy is Vp. And based on that configuration, this is will not be repeated in all problems. But based on the configuration that I have, Vp is zero. Since Vp is zero, I will substitute in that equation by Vp is zero. I can say Vn is equal to zero. Okay. Any other question? Okay, let us see this example. This is straightforward problem based on the inverting amplifier. So he's asking me for that circuit to design an inverting amplifier. I forgot to add in here. So inverting IN. Design an inverting amplifier with gain of 12 volts. Use positive negative 15 volt as a power supply. And an ideal operational amplifier. He is asking you to design that operational amplifier. I know the circuit for that operational amplifier should be something like that. So by asking me to design, he would like me to find the values for RF and RS. Now, if I try to use the previous equation, which is this equation, which is describing the relation between the output and the input. He told me design an inverting operational amplifier with gain which is equal to 12. So this is the gain. It's equal to 12. There is no unit for that gain. So the gain is equal to 12. If the gain is equal to 12, the ratio between RF and RS is equal to, yes. But he is asking me to design that inverting amplifier. So what should I do? Actually, if this is a design problem, I have to have some resistors in my lab. So I'm designing that in my lab. So we are talking about that problem in the lab. So what are the available values for the resistor? So you will try to see what is the availability in your lab. Do you have 1 kilo? Do you have 2 kilo, 15 kilo, 3 kilo, what do you have? And then you will plug here one of those to be what you have. And then you will try to find the corresponding value for the other one based on the gain is equal to 12. If you try to find the other value and you found it's equal to 2.2 kilo, for example, and you don't have 2.2 kilo in your lab, so you will try to find another value for RF. Are you seeing what I'm talking about, guys? So I have relation between RF and RS, and I have some limited values for the resistors. So I will try one value of them and see the other value. Do I have that value in the lab? No. So probably I will try another value, trial and error, based on what I have. Are you seeing that? Any question? So for doing that, what I have to do is, for part A, I will say, since the gain is equal to RF over RS, this guy is equal to 12. If we choose RS to be, for example, 1 kilo ohm, then RF will be equal to 12 kilo ohm. Do we have 1 kilo and 12 kilo ohm in the lab? If I have, this is the end. If not, I will try another value and see the corresponding value for RF. But this problem is not, I'm not giving you that problem in the lab. I'm giving you that problem, for example, if it isn't the test. So you can assume any value and find the corresponding value. If this is test problem, you can assume any value. But if you are doing that in the lab, you have to match what you have. Are you seeing what I'm talking about, guys? Any question? Let us see the second part. What range of input voltage Vs? He is asking me about the range of values for Vs. Allow the operational amplifier in this design to remain in its linear operating region. So he is asking me about the values of Vs that will allow this guy to work in the linear region. What should I do? What should I do?
We have VO between the plus and negative 15, and we have to get VS in order to be like.
Yes.
The ratio is 12.
Yes, I have the positive VCC and the negative VCC, the limits for the saturation. And I know that the gain is equal to 12. And I know that V output over V input is equal to negative RF over RS. And this gain is equal to 12. So I know that VO over VS is equal to negative 12. He would like to find the range of values of VS such that this guy is working in the linear region. So what am I going to do? I'm going to choose the maximum value for VO, which is 15 positive. And then I'm going to choose the lowest value for VO, which is negative 15. And then I will try to find the corresponding VS. So what am I going to do here? I'm going to say for part B, I know that the gain, which is VO here, this equation, VO over VS. So VO over VS is equal to negative RF over RS, which is equal to negative 12. Based on that, I can say VO equals negative 12 Vs. Or in other words, I can say that Vs equals negative 1 over 12 VO. Then I will say if VO equals 15 volts, if VO equals negative 15 volt. What is the value of Vs? Then I can say Vs for positive 15 will be equal to negative 1.25 volts. And VO here, based on negative 15, will be equal to 1.25 volt. Based on that, I can say VO should be in between two values, negative 1.25 and 1.25. Straightforward case. This is Vs. Yes, thank you. This is Vs, which is equal. This is Vs. Let me erase this. This is Vs. So based on that, I can say Vs is in between negative 1.25 and 1.25. Any question for that problem, guys? Yes. Yes, because if you try to read the problem here, he said what range of input voltage that allow this guy to work in the linear region. He would like to find the range of VO. So I'm taking the highest and the lowest value to be VO for the highest value or VO for the lowest value, and substitute by that inside the equation to find the corresponding limit for V input. Because he asked me, he would like to find the range of the inputs. Any question for that problem, guys? I think we started understanding right now how to deal with the operational amplifier. It's a straightforward circuit, very easy and very simple circuit. What I have to know what's VP, what's VN, what's IP, what's IN. And based on that, I can solve any problem related to that guy. Let us talk about the summing amplifier. This circuit is describing what we are calling summing amplifier. So the first application that we studied for the operational amplifier is to use it for inverting my input voltage. If I have 10 and I would like to have negative 12, I can. If I have 5 and I'm looking to have negative 2.5, I can. So I can change the value of the voltage and inverting its sign. That's why we are calling it inverting operational amplifier. This is the first application. The second application is the summing operational amplifier, the summing amplifier circuit. We can use this guy to add some input sources voltage. So if I have like 2, 3 sources and I would like to find the output at the summation of those, I can. Like this circuit, for example, it gave me RA, RB, RC. How many sources do we have? I have 3. The first source is VA, the second source is VB, the third source is VC. This guy, I told you before that, and instead of drawing the circuit, actually, this guy looks like what? This guy looks like something like that. Right? But I didn't draw it. I represented it as if positive, negative VA. And by the same way, this guy has a source. This guy has a source. The source here is VA, the source in this guy is VB, and this is VC. What's RABC? These are the internal resistance for these sources. And I have here RF, which is the feedback resistance. This circuit is similar to this circuit. What is the difference? The difference is, instead of having only one source, I have 3 sources. Which are those? So, what is the relation between the output and the input? Do you expect that the output is equal to the input summation, the input voltage, multiplied by a specific gain, multiplied by negative sign or not?
Yeah.
Multiplied by negative sign, because all of these sources are connected to the negative terminal. So I'm expecting in advance that the output voltage is equal to negative something multiplied by VA, plus negative something multiplied by VB, plus negative something multiplied by VC. And this is what I'm looking for. Let us derive these equations or these terms. So this voltage is representing what? This voltage, imagine this node is N. And this voltage is the same like this voltage. So the voltage from that point to the neutral is Vn. There is no need to write it Vn and draw it. I know it's Vn. The voltage for that node is equal to Vp. So it is the voltage from this to this. What is the relation between Vp and Vn? They are equal. You told me. Vp is equal to Vn. Vp is equal to what? 0. So Vn is equal to, based on that configuration only. I'm not going to say that for all circuits. But since here Vp is equal to 0, I can say Vn is equal to 0. So Vp is equal to Vn and Vp is equal to 0, then I can say Vn is equal to 0. And don't forget, guys, Ip is equal to In is equal to 0. This guy is representing In. This guy is representing Ip. Now, I'm going to repeat what I said in the previous case or the previous application. Summation the current for node N is equal to 0. So summation I is equal to 0 for node N. How many currents do we have? We have this, we have this, we have this guy, which is the summation of those. Am I right? So the current in this guy is Vn minus Va over Ra. So Vn minus Va over Ra plus the current in this guy is Vn minus Vb divided by Rb, right? Plus the current in this branch is Vn minus Vc, you are right, divided by Rc, plus the current in this guy is Vn minus Vo divided by Rf plus, and the summation is equal to 0. You told me that In is equal to 0. So based on that, I can rearrange that equation and find Vo. So based on that, I can say Vo is equal to negative Rf over Ra times Va plus Rf over Rb times Vb plus Rf over Rc times Vc. Am I right? And this is what I expected. Negative something multiplied by Va plus negative something multiplied by Vb, and by the same way for Vc. If you would like to have one gain, I can say as a special case, if Ra is equal to Rb is equal to Rc is equal to Rs, then I can say Vo is equal to negative Rf over Rs multiplied by Va plus Vb plus Vc. This is in case of what? In case of Ra is equal to Rb is equal to Rc is equal to R source. If all sources have the same R, at that time I can say the output is equal to negative the gain multiplied by the summation of the input voltage. Based on that, I'm calling this operational amplifier as summing operational amplifier. So what we studied today, we studied only 2 applications of the operational amplifier, the inverting and the summing. Next class, I will continue talking about different applications for the operational amplifier, like non-inverting operational amplifier and difference operational amplifier. Thank you, and I'll see you on Wednesday. Please don't forget, guys, on Wednesday that